All right, this video is for section 1.2. It's on exponents and scientific notation. So write that down. The product rule is the first thing we're going to look at. It's the product rule for exponents. There's a product rule for roots and product rule for the other thing, but we're looking at exponents here. The product rule that we're usually looking at is exactly this. A to the m times a to the n is equal to a to the m plus n. When we multiply exponential expressions with the same base, we can add the exponents, and it's going to be simpler. Here's some examples of this. First, with some numbers. 2 to the third times 2 to the fourth is, you might not have to write down this middle step as you're doing this, but 2 to the third times 2 to the fourth allows me to add those exponents and get 2 to the seventh. So if you can just go from here to 2 to the seventh, that's fine. Taking the extra step is good because sometimes this will be a larger expression, and just doing that can be difficult enough. We can also have variable exponents, but the only way this rule works, the product rule, the only way it works is when we're taking a product of two exponential expressions with the same base. The exponents can be the same or different, doesn't matter, but it's the same base that makes this work. Here's another example, t to the fifth times t to the third. That's with some variables. And that's t to the 5 plus 3. Add the exponents, t to the eighth. So I didn't write in the detail this time, but I did the same thing. Finally, well, I've got a couple more, but this one, let's do negative 5 to the third times negative 5. And I'm not gonna completely simplify this and actually find the simplified value. I'm just gonna apply the product rule. The base is negative 5. The exponent here is 3. The exponent here is 1. There is no exponent, but negative 5 to the first power is negative 5. But I can do this as negative 5 to the fourth. And it should take another step to completely simplify it, but I just want to do this application of the product rule. Let's look at one more where this time we'll have x squared times x to the fifth times x cubed equals x to the well, I can just add all three of them. You could work with the first two and add those up and get 7, and then add the 3, and that'll bring you to x to the 10th. So the next thing that we're going to look at is the quotient rule. So just as the product is what you get when you multiply things, the quotient rule is what you get when you divide things, and the quotient rule looks like this. A to the m divided by a to the n is a to the m minus n. So again, we've got the same base, but this time we're dividing. And what happens is I take the exponent in the numerator and subtract the exponent into the denominator. What that looks like in an example is, let's look at 3 to the fifth over 3 squared. Applying this rule, it's 3 to the 5 minus 2, and that's 3 to the third. And that's 27, but the only thing that I wanted to do here was demonstrate the quotient rule to simplify it using that. The next step would just be to say 3 times 3 times 3 is 27. The other example I have is a variable one, t to the 23rd divided by t to the 15th. But again, it's the same thing. It's t to the top exponent minus the bottom exponent, and that's t to the 8th. And that really is simplified for that one. So we've seen the product rule for multiplying, the quotient rule for dividing. We're also going to use the power rule for powering, or applying powers to powers. What it looks like is this: a to the m raised to the n is a to the mn. And I mean m times n here. You can put the dot if you want, but we're going to kind of stop doing that so much unless we need to. So the power of the power is the power that's the product. You multiply those two. That can be a little bit confusing. The product rule, you add the exponents. The power rule, you multiply the exponents. It is potentially confusing because you multiply not for the product rule, you multiply for the power rule. Here's a couple examples of this. X squared to the 7th. What it means is x squared times 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 x squared. It's 7 factors of x squared. But I don't have to write that or do anything like that. All I have to do is multiply those powers to get 14, x to the 14th. Negative 2 to the 3rd to the 5th. So there's a lot of parentheses here, but the inner ones are around this middle. That's the base, negative 2. Raised to the 3rd, and then that result raised to the 5th. Again, this is the product rule. I can do negative 2 to the 3 times 5 is 15. And then we could evaluate this, what this number is, but that's the power of the power rule, or the application of the power rule, that gets us a much simpler expression rather than a power of a power. The next thing we'll look at is called the zero exponent. So exponent roughly means how many times you multiply the thing by itself. Specifically, it means the number of factors of the thing that are multiplied together. So x to the 3rd means x times x times x. X to the 1st just means x times nothing. It's just x. But x to the 0 means 0 factors of x. And this is called zero exponent. And it's a little bit, I want to be a little bit more careful with this one. If a is not equal to 0, that's going to be my exponential base, then a to the 0 is equal to 1. And the way to say this more easily is any number to the 0 power is equal to 1. That's almost true. The only exception is, and I'm going to mention this, 0 to the 0 is undefined. It's a power of 0, so it should be 0, but it's something raised to the 0 power, so it should be 1. It doesn't have a good definition. It's not going to come up very often, but it is undefined. For any other number, though, if we raise it to the 0, it's really not very exciting. It's just equal to 1. Often the whole expression goes away. So here's an example that's a little bit informative, just to look at it in a couple different ways. C to the 3rd divided by C to the 3rd. If I use the quotient rule, that's C to the 3 minus 3, which is C to the 0, and that's equal to 1 as the 0 exponent. Now also, you could look at this a different way. C to the 3rd divided by C to the 3rd, whatever that number is, as long as it's not 0. We divide the number by itself, we should get 1. So this is just kind of verifying our expectation that the 0 exponent should make sense in terms of a fraction. Negative 3x to the 5th divided by x to the 5th. For this one, the negative 3 is kind of its own thing. There's nothing similar to it. But the rest of it, x to the 5th over x to the 5th, that's x to the 5 minus 5. Or x to the 0. And this is negative 3 times x to the 0 is 1. So this whole thing is just equal to negative 3. I really think that to effectively use this rule, you should carry this one all the way through to the completely simplified form, because don't leave it as something to the 0 power. Simplify that and make it a 1. And if you're just multiplying by 1, you might as well not even write it. The next thing we'll look at relates to the 0 exponent, but extends in a different direction. Negative exponents. A to the negative n is equal to 1 over a to the n. In other words, a negative exponent means that that thing really belongs in the denominator. So this is a to the n downstairs, but a to the negative n means 1 over a to the n. And there's a special case here. Very important case. When that n is equal to 1. In other words, if I'm looking at a to the negative 1, that's 1 over a to the 1, 1 over a to the first. In other words, just 1 over a. And that's a really important special case of negative exponents. That's what we've seen before. It's the reciprocal. The reciprocal of a is a to the negative 1, or 1 over a, same thing. Here's an example of negative exponents. So starting with this expression x to the 3rd over x to the 10th, I'm going to use the quotient rule to write this as x to the 3 minus 10, or x to the negative 7. But this is not considered simplified most of the time. With a simplified form of an expression, the exponents of the variables should be positive. In fact, probably all the exponents should be positive, but this is an easy fix because it's just 1 over x to the 7th. That's that negative exponent interpretation. There are 2 more rules for exponents, and this is why you really have to practice these. You've probably practiced them somewhat before, but you have to brush up on them because you can't mix them up. That you can't interchange parts of different rules. That doesn't work at all like that. You can use the rules in combination, and that's what you really need to practice at, but they have to be used properly. The next one is the power of a product. And I don't like this name, except that it describes exactly what it's about. It's a power of a product. We've already had a power rule and a product rule, though, so the names really aren't the best way to keep them straight. It's by using them and understanding what you can do with them. The power of a product rule says this: if I have AB raised to the nth power, that's a to the n times b to the n. It's the power of a product. What it means is AB multiplied by itself over and over, n factors of that multiplied together. The thing that's different about this from any of the rules that we've already seen is this formula has 2 bases. Actually, this is a better place to look at it as two different bases. This is a base, AB raised to the n power, but it's equal to a raised to the n times b raised to the n. And that's the power of a product rule. Here's an example with 2t to the fourth. This is 2 to the fourth times t to the fourth. And you can and you probably should simplify the 2 to the fourth expression just to the ordinary number. 2 to the fourth power is 16. So 16t to the fourth. Here's another one that's an application of the power of a product rule. Power of a product rule. It really is called that. It is the power of a product, so the name works, but it doesn't have a special or memorable name other than what it is. So anyway, here I'm going to take the x to the third and the y squared to the third. Now I'm doing that not all at once. I want to be careful and do the steps correctly. Now, so I used the power of a product rule. This is a power of a power. That's where we apply the power rule. The x to the third, pretty much done with that, but y squared to the third is y to the 2 times 3. In other words, x to the third, y to the 6th for this one. And this next one is the final rule of all these exponent rules. It really corresponds to what we just did with the power of a product. This is the power of a quotient. I think it's actually good that there's two rules like this, because if there was only one of these, it would be easily forgettable. But there is the power of a quotient also. And it says that if I take a quotient to a power, I can take the powers of the numerator and denominator separately and then divide. So this says that I should do a divided by b, then raise that to the n power, the order of operations with the parentheses. Here, I can raise a to that power, and I can raise b to that power, and then divide. And this is actually going to help us simplify, usually, more than this form. Here's an example with numbers. Okay, this one actually has numbers and variables. So here's a power of a quotient. Quotient is what you get when you divide. A fraction is another name for it. A power of a quotient. So I'm going to take the power of the numerator and the power of the denominator, z to the 5th to the 3rd. Then 4 to the 3rd is 64. Z to the 5th to the 3rd is z to the 5 times 3. It's a power to a power. That's the power rule. I need to multiply those exponents. Z to the 5 times 3 is 15. And that's it. I have a variable one too. P to the 3rd over Q all raised to the 6th power. So a power of a quotient, and I do that with the power of a quotient rule. P to the 3rd to the 6th over Q to the 6th. And now, again, I have a power of a power. I need to use the power rule, multiply those two. P to the 3 times 6 is 18. And Q to the 6 is just Q to the 6. And so this is what's considered the simplified form for this one. Another aspect of simplified is the We don't want negative exponents. Another aspect is we don't want a negative in the denominator. The negative should be either in front or with the numerator. Some of it's convention, but we kind of have to have a uniform style for it. The next examples that I have are using these rules in combination. And that's really what this section is about. It's not enough to just be able to use these rules. You have to be able to use more than one of them to really simplify an expression. And in these examples, that's exactly the direction, simplify. For part A, I've got the expression 6m squared n to the negative 1 cubed. And I'm going to use first the power of a product rule. I'm going to use a little bit of an extended version because I don't want to do two separate steps. I want to do one step. 6 to the third, m squared to the third, n to the negative 1 to the third. So I did use like an extended version of the product of a power. I have three factors here. It looks like distributing. You know how to distribute. And this looks the same. It's not distributing, it's not called that, but it is the same. You're right to notice that. I'm distributing the exponent of 3 to be the exponent of all the factors. That's not how distributing works. Distributing is a multiple of a sum. This is a power of a product, but it does look the same for a reason. It's actually the same algebraic property. It results in a different kind of thing just because they're different. They mean different things, but 6 to the third is 216. M squared to the third, that's a power of a power. That's where I need the power rule. That's m to the sixth. And n to the negative 1 to the third, that's n to the negative 1 times 3 is negative 3. The only thing I need to do to get that completely simplified is to write that as n to the third in the denominator. So as to avoid a negative exponent. I've got another example that's similar to this one. It says u to the negative 1 v over v to the negative 1 squared. There's more than one way to do this. You can actually simplify the thing in the parentheses first and then apply the power of a product. Here I'm going to use the power of the product and power of a quotient at the same time. It's not difficult if you think of that idea of it's like distributing. This exponent is going to go for this, this, and this. It isn't literally distributing, but it's very much like it. U to the negative 1 squared, v squared over v to the negative 1 squared. I applied you can do it in two separate steps, yes, but I applied the product, the power of a product rule up here, and the power of the quotient rule down here. Now I'm going to simplify this further. U to the negative 1 to the 2, that's u to the negative 1 times 2, or negative 2. V squared, I can leave that alone for the moment, but v to the negative 1 squared is v to the negative 1 times 2, in other words, also negative 2. Now I'm going to fix these negative exponents. What this u to the negative 2 means is that there should be a u squared downstairs, u to the negative 2 upstairs. That negative exponent means it should be in the denominator. Also, the v to the negative 2 in the denominator, that negative exponent means this should really be upstairs. This v to the negative 2 belongs up here as a v to the 2. There's this other v to the 2, v squared. And then I'm going to use finally the product rule right here to combine those to give v to the 4th over u squared. And that's the simplified form. All right, there's one more piece in this section that's worth reviewing. It's really not something that we're going to use a lot in algebra, but if you take chemistry, especially, if you take physics, geology, a science that has a lot of math in it, but also data, they use scientific notation a lot. And it gives us ways of writing down numbers that are either really, really, really large, like a billion, I guess is kind of large, or really, 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 really small, like 1 over a billion, 1/1000th. So scientific notation gives us a better way to talk about these numbers. And it looks like this. We're going to have a number times 10 to a power with two conditions here. First, the number needs to be between 1 and 10. And what I mean by that is that its size, or its absolute value, needs to be greater than or equal to 1 and less than 10, not less than or equal to. What this really means is that A is going to have one digit to the left of the decimal point, and as many as it wants to the right, but there's only one digit to the left of the decimal point, and it's not a 0. That's really a number 1 through 9 point, whatever the rest of the number is. And then times this is really an expression for the magnitude, how big the number is. N is an integer. It can be any integer, positive, negative, 0 even. Here's a couple examples of what scientific notation means. First, 4.7 times 10 to the negative 6th. I think you'll notice when you look in your book, they use the multiplication cross. I don't like to do that. I use X too much. So when I write a multiplication cross, the first thing I think is that that's an X. I'm going to use the center dot. Now the lower dot is the decimal point. And this is the number A that I was talking about. It's between 1 and 10. It's got one number to the left of the decimal point, and then, well, this one has 1, but we'll see some that have more than 1 to the right, but there's one number to the left of the decimal place. This means this number is how many times I need to move the decimal point, or how many places I need to move it. So what I can tell is that 10 to the negative 6, that's 1 over 10 to the 6th, or 1 over a million. Very small number. This is going to result in a very small number. It's 0.0000047. I know this because I wrote it down earlier, but I usually, when I'm doing this, have to start here and count this way the number of places, the number of decimal places. So 4.7 would go to 1, 2, 3, 4, 5, 6. Negative 6 power. Small number. 0.0000047. This is a more graceful way to write it and an easier way to read it. Here's one that's big. 3.175 times 10 to the 4th. Not too big, I hope. Here's my number A, my number that's, well, you know, we haven't had an example of this yet. Let's make it negative. So my number A is not between 1 and 10, but its absolute value is between 1 and 10. It has one digit to the left of the decimal point. It's a negative number. That really doesn't make much difference for the notation. It just means that the number is negative. But this one has a positive exponent. This is 10 to the 4th. 10,000. And what this is saying is negative 3.175 times 10,000. It's big. In particular, it moves the decimal point 4 places from where it is here. If I put my 3175, I need to move the decimal place 4 places. 1, 2, 3, 4. There should be another 0, and there is another 0 there. That's a placeholder. I don't actually want to put the decimal point. If it's just the end, it looks like a period. You don't need a decimal point for this, but you do have to move this decimal point 1, 2, 3, 4 places. So I do need that 0 as a placeholder. 3.175 times 10,000 is 31,750. That seems reasonable. Here's a couple examples of changing. Let me keep this here to refer to, but here are some examples of changing a number in standard notation into scientific notation. So converting it the other way. This is going to be 9.6214. I'm not going to write that 0. Now, whatever your chemistry teacher tells you, that's what you should do in that class. But for math, I don't want to write extra zeros. This one I need as a placeholder, because that's a different number. But when there's extra zeros to the right of the decimal, they don't really mean anything to me. In chemistry, they're called significant digits, and they do mean something, but not for us. This is the number between 1 and 10. And then I need to do times 10 to the, well, it's going to be a positive power because this is a big number. 1, 2, 3, 4, 5 places. I need to move the decimal. So that needs to be 10 to the 5th. Here's one with a lot of counting. Well, kind of a lot of counting. This is a very small number. 0.000000. That's 7 zeros after the decimal point. This one doesn't really count. It's a placeholder more than anything. 7 zeros and then the 1. So my number part is going to be 1.3, number between 1 and 10. 13 is too big. 0.13 is too small. 1.3 is perfect. Now the number of places that I need to move the decimal is what's going to go up here. 1, 2, 3, 4, 5, 6, 7, 8 places. So this is 1.3 times 10 to the negative 8th. I know it's a negative exponent because this is a small number. Large numbers have positive exponents in scientific notation, and small numbers have negative exponents, a negative power of 10. Now on your calculator, there are keys like E and notation with a capital E on the display. That means times 10 to the this power. So what this means is 3.5 times 10 to the 14th in this case. If your calculator gave this as the display, for example. The display uses the capital E for exponential notation. The exponent is 14. The base is always 10 for scientific notation. This is the button that the calculator has. It's a double capital E, and you use that to type things in the scientific notation. You can type it into your calculator really almost just like this. You would just press this number and then the double E button and then 5. You don't type the base or the times or anything. It's just all you have to put in then is the exponent.